This is David Spears, Civil Engineering Instructor at Texas Tech University, talking about CE 2301 statics. We've got a 3D equilibrium problem here, solved for the force in the cable. We're given that we have a rigid bar ABCD going from, lies in the XY plane and supported by a ball and socket at points A and D, and this cable BE. We also note that we have an applied force out here of 85 pounds. The coordinates of all those points are given, and we want to find the force in the cable BE. So the basic steps of these 3D equilibrium problems are pretty much 3 steps. Do a free body diagram of everything. Express all your forces in Cartesian format. That is the sum of the forces you'll see down here. And then perform the equilibrium equations on it, which is primarily the sum of moments equations, which we want to use to eliminate unknowns. Most efficient way to do it. So, like I said, the first step is to do a free body diagram. And so over here I've done the basic free body diagram. I've eliminated my coordinates and my points or anything like that just to make it clearer. It's just a rigid bar ABCD. And at A I have a ball and socket which allows rotation, so it provides no moment resistance, just forces to prevent translation, AX, AY, and AZ. Do the same thing at point D where I have a ball and socket with DX, DY, and DZ. I have the force in the cable, which is a vector, which I'll express as TBE. And then I have my 85-pound force. So the free body diagram really lays out everything so I can see what's happening with this bar. Step 2 is to get everything in Cartesians, and I've really only got one thing to worry about for Cartesians. That's the force in the cable. So the force in the cable from the equation sheet is it's a vector, and it's the magnitude times a unit vector in the direction of the cable. And given it letters for the endpoints, it's the unit vector is u e over b, because the tip of the vector, I can look at my free body diagram, the tip of my vector is directed at point E, and the tail of the vector is at point B. So I need u e over b, and that is really a position vector, r e over b, which is a vector divided by its magnitude. So tip over tail, tip minus tail for the coordinates. For B to E, E is the tip, the coordinates of E minus the coordinates of B, so it's 0 minus 4, 0 minus 5, 6 minus 0. I've written that up here. Then the magnitude of it, it's the length of it, it's the square root of the sum of the squares, which 4 squared, 5 squared, 6 squared works out to be square root of 77. And I do the math, and I get this unit vector, negative 0.456, and so forth. That is the components of my force vector TBE. Put all those coordinates, and they are all multiplied by the overall magnitude TBE in the cable. The other forces acting on this rigid bar ABCD are the ball and socket reactions at A and D, which are just force reactions, AX, AY, and AZ, and same thing for D. I don't know any of them, but those are the variables that represent them. And then I have the force vector, the applied force, which I've called F, is just 0I, 0J, and negative 85K pounds, because it's a downward force. Now I've got everything in Cartesians. I'm ready to move on to step 3, which is equilibrium equations. Everything is in equilibrium in this statics class. So the sum of moments about everything is equal to 0. So we could sum moments about point A or D, or really about anything, the origin, and we have enough equations to solve for it. But as engineers, we always want to find the most efficient way. And so we want to sum moments about a line to eliminate unknowns, and that would be line AD. Of course, A and D, the forces of the ball and sockets provide no moment because they intersect that line. The only thing that causes moment is the force in the cable, TBE, and the applied force, 85 pounds. So I draw another little diagram over here, and I show my line, AD, and my other two forces, TBE and the 85 pound force. Okay, so what I want to do is remember from my equation sheet that the moment about a line is a dot product with the cross product, and the U, I need a line over that because that's a vector. That U is a vector, and so I need a bar over that one too because that's a vector. Anyway, the general format is I get a 3 by 3 determinant, where on the top row I have the unit vector representing UAD and dotted with R cross F. And remember that R, the position vector in this cross product, can be from any point on the line, I'm taking moments about, to any point on the force. So I want to use that efficiently to get the simplest position vector I can, and you'll see that here, so I have as many zeros in my determinant as I can get. So the first thing I need to do is get a unit vector. It doesn't matter which direction. I've chosen from D to A, but I could easily go the other way and get negative signs. So over here I've done the work. I have written the coordinates of A and D so that I can show the unit vector is the position vector divided by its magnitude. 4 minus 0, 0 minus 7, and 0 minus 0 on the top. Square root of the sum of the squares is square root of 65 on the bottom. Working out the math, I get this expression for the unit vector from A to D. You can see if I chose from A to D, I would get negative numbers in all these. Everything, the signs would be reversed. Okay, so now I've got everything I need. Really, I've only got two things causing moment about line AD. The first one, let's look at the moment about a line AD caused by the force 85 pounds. And that's just the unit vector dotted with R cross F, but I want to choose my R position vector, have as many zeros as I can get, so I just want to go, I could go either way with this one. I've chosen to go from point D, a point on the line, to point C, the point where the force is applied. So I've got the unit vector on the top, and then I've got C over D down here, which is the coordinates of C minus the coordinates of D, and that's just from up here 4 minus 0, 7 minus 0, and 0 minus 0, so I get 4, 0, 0 for that position vector. On the bottom row I have my force vector 0, 0, negative 85, which is coming from up here where I've expressed all my forces in Cartesian. Only got one term, and remember that this is a scalar moment. This has no Cartesian components. It's not a vector, it's just a number. So I evaluate this determinant. I've only got this middle term, negative of negative 0.868, blah, blah, blah. Works out, do the math, negative 295.2. My units are pound feet. The other moment about AD is caused by the force in TBE. That expression is UAD, the same unit vector for the line AD. This time I have a position vector. I could choose from D to B or from A to B. Well, A to B gives me a simpler position vector with only one component, so that's the one I've chosen. It's RB over A. And it's the coordinates of B minus A. 4 minus 4 is 0. 5 minus 0 is 5. And 0, 0 minus 0. I get this middle row for my position vector, RB over A. And then I put on the bottom line, I put my force vector components, which are coming from up here, where I've expressed TBE as Cartesians. These are the numbers. Once again, I only have one term to evaluate. This positive 0.496 times this little 2 by 2 determinant, 5 times 0.684 TBE. Everything else goes to 0. It's nice, so I get 1.696 TBE. And so, in summary, the only thing causing moments about AD are those two moments. And I've got 295.2 negative plus 1.696 TBE. TBE works out to be 174 pounds.